Okay, hello everyone. Excuse us for the delay. We had a little bit of a technical issue, but it's solved now, so we can get on the go with today's presentation. Thank you everybody for being here in person and on Zoom in this new Cat 7 lecture. Today we have Professor Dessouky. Professor Dessouky is a professor at University of Texas at San Antonio's Department of Civil Environmental Engineering. He is the Associate Director of the Transset Regional University Transportation Center and a professional engineer. His research focus is in innovative technologies for harvesting power from transportation infrastructure, and he has more than 20 years of experience in pavement materials, transportation sustainability, and traffic safety. Professor Dessouky obtained his doctorate in civil engineering from Texas A&M University, and he was a postdoctoral researcher here at ICT. And I bet Professor Alcani has maybe something to say about that.
Okay, yeah, sure. Where can you hear me? Yes. We're very, very pleased to have Professor Dessouky with us. He's been a couple of years here as a postdoc, and I had the pleasure to serve on his committee. We're very impressed of his research record and his accomplishment at his university, and he's considered now one of the leaders in this field. And we're very, very pleased to welcome you here again at the University of Illinois. We missed you here, but you're always part of us. So thank you for being with us today.
Thank you all. Thanks for having me. Thanks, Dr. Alcani, for inviting me again to ICT. That's where I started after my PhD for 20-year great time of my career. I learned a lot. Some of the work you're going to see today is based on the work that I learned and I practice here at Electro. Great experience, great time, and I'm glad to be back after 14 years. Great to see the center growing and seeing you all in the right place. And really, you're in very good hands here. You're going to learn a lot, like I did. I'm going to show you some of the work that I started at UT San Antonio. It's on methods to harvest energy from the pavement. Pavement materials, as you see in the introduction, all what I do is pavement materials, pavement design, pavement analysis. And then at some point I thought maybe I can take a look into the pavement from a different perspective. Infrastructure that has been there for over the years and has been used to us to move from one point to another. Maybe we can take a look at it in a different way. So I'm going to show you here, this is the group of students that have been part of this journey. A collection of students from electrical engineering, mechanical engineering, material science, and they're all from UTSA. They all work together to come up with products that you're going to see today. I will never be where I am right now without their contributions, their work, their expertise, their hands-on. Everything was done in-house. Their focus, their mentality, their initiative has to be things done. And again, to the funding agencies that allow us to make these products happen. So here is where I see the future coming. Pavement have been always the infrastructure to allow us to move from one point to another. Once we move, we improve ourselves, we improve the economy. At some point, we got to acknowledge that this infrastructure, somebody else is taking care of them for us, which is the deep. So their perspectives are different. Their perspective is to make sure that this infrastructure is healthy, sustainable, and continue to deliver what they're supposed to deliver. So at the same time, we want to make sure that these infrastructure can work for as long as they're being used in service. So here is, if you put together some of the challenges that we have in pavement roadways, while material is one part of it, but I again looked into a different perspectives from it. So you can see traffic congestions. I'm in San Antonio. I'm not surprised to see traffic problems. You're glad that you're in Champaign, you didn't see that. Traffic and pedestrian safety. I'm engaged a lot with TxDOT safety research where we get to have a database of all the crashes that happens every single hour. We put it all in a database for us. We're about 600,000 crashes a year in Texas. About 10% of that in San Antonio. And we get fatalities, about 3,000 a year. all happens on the roadways. So that's a problem. Roadways has to step in to find the ways to try to avoid that somehow. Some part goes onto the driver, but again, what can we do for the pavement as well? In urban island, I'm in city zone, so I see this problem a lot. Raise in air temperature. I talked to Dr. Jeff earlier this day. This is a problem. So we see it. There's air pollution that comes with it. We acknowledge it's in there. What we can do about it as well. And then finally, connectivity to rural areas. I'm in urban zones, but if you look into those small towns, which is not reachable to San Antonio, they don't have the same level of service that big cities have. So what we could do to connect them to it. So here is really the ultimate goal, smart roadways. I'm almost embarrassed to see how the auto industry have been innovative their vehicles. So anything above the pavement have been innovative. And we see electric vehicles, autonomous vehicles, CAVs, and all this coming to the market, and there is huge investment, but nobody really looks into the pavement down. So, but the goal of the smart road is really to look into many perspectives altogether, from V to I, how to make the pavement to collect, interact, transfer data to not only to traffic management systems, but to vehicles itself. So it's called vehicle to infrastructure systems, road sensing and data collections. This platform has to be collecting data. It doesn't just have to be a platform to travel. It has to be also collect the data that we are using it. The more data we know, the more knowledge we can improve that infrastructure. And data nowadays is king. The more data we know, the more we have over control of this infrastructure. How we can make them less congested. If they are smart road, they can communicate with vehicles, it will reroute vehicles around. So these vehicles needs to have data from pavement somehow. And then you have to look into cooling pavements, ideas. Once you get the area, the energy out, how that affect the energy in the pavement, smart lighting, safety of pedestrians, prepare workforce. You guys are the next level, the next generation's workforce. You learn about these technologies, you go out, you implement it, you spread the word, it becomes our tradition or our common research later on. So I looked into the pavement from the perspective of what we learned in school. We have thermal energy that goes into the pavement. Every day, the pavement collects a lot of heat. You looked at the surface, you looked at the bottom layers, there is always the thermal gradient, the difference between the top and the bottom. And that difference about 20 degrees. You look into the records, you look into the data, you collect your data. These thermal gradients all the time in the pavement. I'm talking about asphalt pavement. And then you get strain energy. Loading imposed from traffic that goes into the layers. So there is some kind of a deformation the pavement will collect, but there is always force deflections. This strain energy goes and absorbed into the pavement. So all those together happens every single day, as far as we have traffic, as far as we have heat. And we do have both. So we came up with ideas. We put them, we just not an ideas. We make them. We produce them all in the lab. Ideas to solve slow speed zones, urban and low volume roads to collect power, heavy traffic solution ideas, intersection solutions, all ideas, all about, started with energy harvesting and sensing. So we'll try to go through some of them. I'm going to skip this one quick because we have a glitch in the videos, but here it is. The concept is we're going to build a platform, a small platform of energy harvester that allow the following. When vehicle drives over it, it will insert mechanical loading on those piezoelectric stack, which we call it. Once you put them under mechanical pressure, it will generate electric voltage. And that electric voltage, from this point on, I will bring in an electric expertise to come in on board to help me build this. A DC-DC converter, a battery storage, a microprocessor, to take the voltage and store it. At the same time, since I have a source of power, stream of source of power coming every time I have a traffic loading, it allows me to have a memory, a processor to transfer the data that comes in. what data we have, you see it. Load, vehicle, speed, directions, and count, which what the DOT needs to assess the pavement structure. What does the sensors look like? Stacks of pieces like this, which once you put them under pressure, it will generate voltage. But you have to stack them in such a way that you collect the positive with the positive and the negative with the negative. So you transfer the voltage from one side and the negative from the other side. And you add that all together and you connect them, and you have a stream of electric voltage continuously during as far as you have traffic loading. What do you put them in the pavement? No brainer. As close as possible to the surface, that's where you get the maximum stresses. So we had to learn a lot about it, and we had to test them in the lab. The traditional research ideas, let's come up with a small prototype. Let's see how we can find out what is the expected output that comes with it. So we built a stack, we built a small enclosure, we tested in the UTM, the asphalt machine. A lot of you are familiar with it. We put it under different loading. We check the current, we check the voltage, we check the power. And see, the more stress, the higher the power. So the challenge here is my loading from the traffic is fixed, because we are limited with how much loading. But you can play with the cross section, the design, to maximize the stress and eventually maximize the power. So you can optimize based on the design of the sensor of the piezoelectric transducer that you get. And then analysis, how much loading we get from there. You run simulation, the finite element, this is US 59, Laredo. This is Northeast. This is major corridor. We got A&M on board. They give us all the layers. We checked with the, so this is what I learned here in Petro, by the way. The 3D moving, we load on 3D dimensions. I learned this here. So that's all done in-house. So you can get the stresses over where you're gonna insert the box. And here is the plan. That's the implementation side. The idea is to insert them under the wheel path. So big trucks like this will be all the time driving over them. So you always have the stream of power coming from. It's easier to put them in the right edge because you can collect that too, a battery, a light, a data management. So you can do a lot when you put them towards the right hand of the shoulder. I can keep this since we don't have time. You tell me by the end, if we have discussions, what is the problem with this? Okay, from a DOT perspective, leave it to the end. Here is the system after we put everything together. And I had discussion with the group earlier. Here is what we have. Here is the stack. This is one by one. It's an enclosure like this. A stack like this with the transducer in the middle, thermal energy harvester, and maybe I can use this mouse here. Thermal energy harvesters at the corners to supplement the power in case we don't have traffic. Microprocessor, it collects the data, but it processes the data. So the load will be transferred into certain stress, the speed will become in certain units. And then we have here wireless communication node. The data will be collected, will be stored, but I need to transfer the data out. So we have a node connected to a gateway. So we can transfer the data within, so far, reach 2 miles. So think about 2 miles, that's not much, especially if you're looking into rural areas, which is more than that. But it was a good start. At least we reach to the point that we can get to 2 miles. You can always put in SIM card, and you can get access to the data anytime, any moment. But we said we're going to do completely self-powered. Based on the power we get, how much we can instrument our system. And sensors will be collected. So this is by itself is a sensor. It can give us the load, the speed, and the count. So we got those together. And you can add to this here temperature sensor, moisture sensor as well. So you get additional data within the pavement. Some of the application, we looked at it as well, wrong way detection. While this is major problems in the highways, I would say Texas, and we have several incidents like this every year. Not as many, which is gladly because this is fatal incidents, but having those systems along the ramps, which is the entry points for wrong way driving, that would trigger in right away. That's a wrong way detection or event that can call in a 911 call immediately. So you can pick up here one of the major problems that we have. Eventually, this has been transformed now into an equivalent to weigh in motion system. A weigh in motion is a commercial system that collects loads from series or trailers, commercial vehicles. But now, this is a fraction of the price, can collect much more data, and can be implemented elsewhere. It has to be connected to anything. It is self-powered, so I can completely negate that, which is the power system, and I can have data collected all the time, transferred wirelessly, and I put it anywhere in the network system. So now this is another solution to practically to weigh in motion, the way it is right now. So this is a small video on what we did now after testing everything, having every student coming with a piece of the puzzle, put them all together and run it in the lab. So we drove over it. And then we built a small platform instead of digging in concrete. And then the moment this is a 6x6 platform, and you get the power output coming from it. And eventually, if you have an amplifier, you can now have a stream of LED lighting just from the load. So now by itself, you do have enough power for LED lighting from that system. So what the LED lighting is going to help, maybe I'll show you that in the next few slides. Other solution came in because we have some logistic problem when we present it to the DOT. What we're going to do about it. So we got some feedback, and then we thought about another concept, a concept that I was motivated with from a Virginia Tech professor, I believe you invited here, to build electromagnetic speed bump. So basically, we had incidents of students get killed while crossing school zones, which is not the intention because we always has the slow speed signs. So we thought about, okay, let's have a speed bump that eventually you drive and it can move with you. So the purpose of the speed bump is it is going to be above the surface. So any driver coming in has to slow down. So the concept of slowing down and forced slowing down in drivers will be taken care of. It is now what I can do to get benefit from that. It's a loading. So we build the mechanical system completely under the speed bump. That's going to allow harvest load and energy from it. And basically you can see it's all mechanical components. By the way, this is all done by a PhD in civil. No background in mechanical, completely. So there is no barriers for us, by the way. There's no barriers. Pistons, spring to support, to retract it again, motor, gearbox, and clutch. So you can see how it works. We did our finite elements, we did our lab testing, and this is the UTM, by the way. That's what machine. Other application. We tested in the lab. We dug in our campus, and we built it and we insert it. And that's how the concept is. So this is still a speed bump. You can lift it up. It is above the surface. But when you drive, it moves down. So eventually we expect that when a driver coming in, you see yellow rubber above the surface, they will slow down. So it is still a speed bump. At the same time, you still can drive in a slower speed, but I'm going to take advantage of you driving over it to push the mechanical system down, and I'm going to get the power out from it. I use that power for application. So we drove several vehicles, and here's the power output we got. Depends on the component, which optimize several times. You can get here every pass will get you about 4 to 6 watt. This is 1,000 times more what we got from Piezoelectric. And again, you can always play with the component that you have in the speed pump, which are these. Always play with it. You optimize it to see how you maximize the power. It's all about how much power you can get with how much price you can use to build that system. Applications, school zones, slow speed areas, residential areas, with the expectation of instead of the regular speed pump, it's electromagnetic. I wouldn't say smart speed pump, just electromagnetic that helps produce power. You can connect to flashing beacons later on. You can build in detections that can open up a flashing beacons ahead of time for the driver to slow down. But you have a source of power from you driving on pavement. As simple as that. There could be some logistic problems. Can I just bring this down? I don't want to have it to function. We can lock it in so it becomes flat with the surface. So you can drive without having to slow down. So you can always play with it. And then we came to the concept of the thermal energy harvest. Some of the logistic problems that nobody wanted to mess with the pavement, and really having to play within the lane mile is not acceptable by a lot of DOTs. So you really have to look into another concept, how to avoid the lane mile and work elsewhere. So this is the other concept, the thermal energy. And whether you are in hot climate or cold climate, apparently you still have a thermal gradient. So this could be Champagne. This is San Antonio. You still have that thermal gradient all day long. So we thought about this because the natural landscape have been changed from green to pavement. You have about 70 degrees raise in the surface temperature, which contribute to the heat of an island. This is common in Texas roads if you drive from the heat. So I know that I have that thermal gradient all year long. This is a Houston road, and a difference of 20 degrees. So let's come up with this concept. I'm gonna open this up. Okay. I know this is hot here on the top, and it is colder down here. So I'm going to build a thermal conductor to transfer the heat from the top to the bottom. And that's for the purpose of integrating what we call TEG, Thermo-electric generator, which is right here. For those on Zoom, it is right here. This thermoelectric generator has a very good advantage for us. When you have a difference in temperature from one side to the bottom, top side to the bottom, it allows you to create electric voltage from it. It's a thermal element that works that way. A heat from top, a cold from the bottom, the difference in that temperature allows to create electric voltage. So again, that's another source of power, can be implemented in the shoulder side. I don't need to have any loading. Forget about the tire. Take care of that sensor, take it out. All what it does, it's gonna transfer the heat from top down to that. I'm gonna put a heat sink to maintain the cold side all day. And that difference is gonna allow me to produce the same power I got from the piezoelectric. But now, no loading needed, just from the thermal heat. So that works, should work. Because again, I'm not gonna mess with the lane mile. I can put this on the edge of the road. So we went to cut, we introduced an L-shaped, this is a Z-shaped design. We cut it down, we built our prototype, we cut it, we paint it, we cover it, we let it work. And here is the output. So now I have twice what I got from the piezoelectric. Still milliwatts. But the milliwatts for us is a lot of advantage because it allows us to run sensors and LED lighting. At this stage, that's good enough. I don't need more. This is all new technologies. We don't know how much power we're getting, but at least we get some power that can help with some applications. So here is the concept. So we're going to make this along the shoulder. It's going to continue to produce power all day long, as far as I have thermal grade. And no matter what you do, this is going to work daytime mostly and some nighttime. So we've been advancing the insulation box. We reduced the size. We put our TEG in one side. We backed it up very well with some NASA materials called PCM to preserve the heat. So we maintain the temperature on one side all day long, no matter what happened to the soil. And the heat source keeps going up over the day. So we always have the gradient, and we always have the stream of the power. We build it in the lab. So instead of me waiting outside and having the system to be installed, we control with the light to control the heat. And then we have several prototypes of the TEGs. We try different sizes to see which one's going to work better. We play with the sizes of the copper plates, the best conductive material we can get. And always look into alternative materials. If you know better, go ahead and try. If you read the papers, we try different dimensions, different materials, but there is always, the room is open for more advancements. We tried it out, and the same LED source of light would come in, just from the heat. If it's able to light an LED, it will activate sensors at any time, because this is very low watt applications. So this is again soil, pavement. Our design is inserted, so you can collect the power. The gradient is maintained, the power is collected. Here's the applications. Minimum LED lighting for our stop signs. Self-powered from the pavement. No need to solar panels, no need to connect it to the power grid. Rural application doesn't have any of that. Yes, solar panel would work better, I agree. I'm far away from the technology of the solar panel. I'm still here. Solar panels have been developed over the years. But I'm talking about an existing platform that can produce the power by itself, connected to those LED applications, and you have this light can come up at any time. How that help in the safety? Imagine a dark sign, a flashing sign. I drive a lot in South Texas and I see areas that have nothing. So if I have this, I will definitely stop. I missed a lot of stop signs, by the way. And then motivation with some of the solar roadway that I've seen and I've read and I've visited. This is France, Netherlands, China. Admire with the concept of having a full applications of solar roadways. I guess this is the future. And if we just keep waiting until things like this will happen, it will happen. Somebody has to go and try. This is a thin film, it's not a solar panel, thin film with a texture. So it does have the texture that you expect from pavement, and it doesn't have a thickness. This one is a solar, you can have very low light traffic, lighters. China did one regular solar thin film, but transparent cement concrete. Maybe Jeff would know more about it. Can have the light transmission through it. So we have the rigid surface, the thin film under. So produce power, and you still have traffic flow. I don't have the capacity to do a lot, but I said, let's do this. I'm gonna build a very small wood frame. I'm gonna get thin film solar. I'm gonna have to design and come up with polycarbonate sheet that's transparent, it is solid, can withstand traffic, so rigid that it's gonna be more rigid than the tempered glass, and transmit off light. And I'm gonna insert it in the pavement. I wanna make sure I collect power anywhere in the network. Again, this could be on solar, on light pole, stop signs, yes, you can. I just wanna use the pavement itself. Let's say I don't have signage. then I can do it on the road. They are all in the roof. Let's bring it on the road. But you expect to have stability to it. So we thought about the glass, transparent polycarbonate glass that allow us to do this. So we run transmission tests to find the best sheet to use. We went out in the campus to test them out. This is a built technology, the solar thin film. So the power is already there. Then we tested under a vehicle. Keep going back and forth, see how long it's going to stand. So it really stands good numbers of traffic loads. So the problem of being cracked is not going to happen. But the other problem of losing the transmission ability, because it's going to get dirty with time. So we took this, you can see this is the power, depends on the quality of the thin film that you get. And this is when you drive the vehicle. I don't use this because I'm expecting you have here, but you see my fingers, right? Transparency test. Some of the class didn't do well after a couple of tests. Some did very well. So 83%, 81% after running the field test, I still have very good transmission. So that filter what is the best class than the others. And here's the application. Intersection crossing for pedestrians. We have massive number of injuries and fatalities at these zones. Some of the zone doesn't have signage. So having this very small, which I believe you can find some of those already in the market, but never in the mentality of collecting power and light LEDs along the way. So a pedestrian will cross and these LED will pop in, triggered by walking on that pedestrian. So a vehicle will come in, you'll see massive lighting here, it's going to slow down. So applications. So problems, solution. Okay. And then the final one. The final one was, this is 4-leg stop sign intersections. Texas. You see nobody. You see the lights, flashing beacons, solar panel. This has been mitigation technologies over the years because of the T-wall. Nobody will notice a stop sign like this in the middle of night. So everybody will just miss it. So we get fatalities. So first solution, you know the flashing beacon, right? Solar panel here to flash the LED. Okay. So we get a lot of those that doesn't have mitigations yet. If you put at why we don't have a traffic signals, it's very costly. Not every road will warrant this if you go back to the traffic design. And this is the economic loss for the number of fatalities we get in 1 year in $1 billion. This is the cost per death in Texas, 10 millions. Actually, in the UTSA, that's the cost per death. With discount, this is the total loss. So what we thought is this, a solution. A thermal detection that can be on a sign, whatever sign. You have a thermal camera, infrared, that can detect a moving vehicles. This is invasive now. So basically what you have, once the vehicle drives, there is heat at the tires, heat at the engine. So the thermal camera is going to detect that. It's going to detect the size of the vehicle, the speed of the vehicle, the direction of the vehicle. So you can separate two directions. At the same time, we have an algorithm that allows us with the digitizations. So everything, every pixel you see in this picture is digitized with the temperature. When the vehicle comes in, you detect, I don't know why it does not show, showing here. It can detect the temperature changes. So as the vehicle moves in, you can detect the temperature change, the size, the speed, and the directions, all with machine learning principles, all done on a small app on your phone. So we had two students. One student built to focus on the testing of the camera, and one student built the macro loading on the phone. This is two students' project, two theses. Here is the application. Any stop sign, if you look at the traffic management MUTCD, before the stop sign, there is a warning sign ahead of it, 200, 300 feet ahead of it. So we expect to do the following. Put the sensor of the camera right here. Once the vehicle comes in, it will be detected. A Bluetooth is going to trigger a flashing beacons on the stop sign ahead. So I want to show it to you. Here is the vehicle. That's where we put in the detector. A Bluetooth sends the signals to these flashing beacons. So this vehicle, assume no lights, by the way. I'm cheating, but this is the cameras. The vehicle will come in from here, will be detected. It's going to send a Bluetooth to trigger the flashing beacons. So a regular stop sign now is going to flash only when a vehicle comes in. It's not just to detect all day, only when a vehicle comes in. So a driver like me, which I missed a lot of stop signs, if I see something is flashing while I'm driving, I will probably going to slow down and stop. I would say about myself, because we run several cycles around. Okay, slow vehicles, high-speed vehicles. We try every concept to do at night, and that opens up to us a lot of other applications. Detections of pedestrians on campus. So we use the same concept. We hang it over one of the light pole, and we're able to count pedestrians on campus. Same concept. Human beings moving, detect the heat. And we use that also for railway application. But I didn't have the chance to present it here because I don't have really the time. Okay, so this is really the output. We came up with problems. We put together the plan with the students. We made a focus group. Every student does one thing, and that's his or her thesis. Then we put things together, test them in the lab. We took them to the field to try it out. And then we have solutions. We expect this solution will have application to improve. Yes. So the heat urban island, my goal was for one of them, once I suck heat from the pavement, I'm expecting to lower the surface from 1 to 2 degrees. So we had a mechanical engineer to do finite element on this. And yes, we found a reduction of a fraction of a degree on the top surface because you're sucking the heat down, right? So you transfer the heat from the top down. So what happened to the surface? Gets less. Still, we need to look really further. Does it really hit and does it really lower where you install your copper plates? What happened to the nearby areas? So scalability is a key and how we expand this. So I'm still looking into the material that I can spread out in the pavement to collect the heat out. Try to be on time. So I'm done. Thank you. It's 35 minutes, but I can 42. Yes, please.
Thank you for the nice presentation. Really strong work by your team and your students. Curious about the camera. Is it being powered by a harvester?
That's another thing. We try a different concept. So instead of complicate things to us, we have a solar panel power to it. Okay, but we proved the concept. We're able now to integrate the thermal energy to this camera, so I can eliminate the solar panel. So it's either you try a lot of new ideas all the time and you figure out whether it's going to work or not, or let's try one concept, get advantage of whatever available, prove the concept. When it works, now let's go back and try to make the optimizations. So now we can cut the solar panel and we can put the thermal harvester. The stop sign have been having a lot of interest. So we patented this, and then Siemens bought the license, and now we are in the position of marketing it out. But again, they bought the license, so they will take care of it from now. We got 2 other patents on some of the devices that we did. The piezoelectric becomes a way in motion now. So we patent this to become a wheel motion alternative to expand it to the roadway network instead of having only commercial ones. Yes.
Thank you for the very nice
No problem.
presentation, Professor. Amazing work. I have a question about the fatigue life of piezoelectric transducer fluorescent. And does it like really present a problem when they are like when they are worn out? A problem to change them and the pavement?
We test this 200,000 cycles. Okay, we could test it even further. We found no degradability or fatigue in those. And they are very stiff, very solid, and they can stay as long as you keep them stacked, vertical, no bending. And that's why we built, because we realized that if the only way they can get break if they lean. So we built a nest, enclosure to maintain them to be completely vertical the whole time. As far as it is vertical the whole time and it's protected from the water infiltration, that's why we have a seal here and we have a seal enclosed. It's going to continue to produce the power unlimited time, because the testing we've done ourselves in the electric groups have been proving that this can continue to function without the need to replace them. I'm not worried about the piezoelectric in a system like this. I'm worried about the battery that I need to replace every once in a while, and the sensors that can eventually get worn out because of the exposure to heat all day long. Although they have advanced the sensors from the electric group, that's what they say, they have advanced sensors now, and they make it too small. I mean, they made a very small robots and they get a pattern on it actually. So this is never a problem with the sensors, but it's the battery. Yes.
Thank you, Professor, for the presentation. I just have a quick question about the actuated stop sign you showed at the end. So I was wondering, how would the performance change with the electric vehicles? Because as you showed in the video, most of those cars were internal combustion engines.
The heat, right?
Yep.
That's a good point.
Yep. Yep.
The heat comes from two sources, from the engine and tire pavement interactions.
Okay.
So if I'm not detecting the engine, which is the motor, I will detect the heat. I will detect the heat and the pavement interaction, which I still can be there.
Okay.
How you separate the pavement temperature from the pavement, that's why with the algorithm, you can always put a threshold on the temperature. You separate the pavement temperature, because it's always high, from the heat that generates about the tire and the pavement. You can always detect the heat from the top of the tire. So it's always going to be there.
And just a quick follow-up question.
You see, you're thinking about tomorrow. When we think about this, we think about Ford F-150. Very common. Yes.
A quick follow-up question. Why did you not decide to go with sound of approaching vehicle?
That's a good idea. That's really a good idea. You can try. I thought about two things: heat and loading. Right? The door is open to try a lot of ideas. The wind, the sound. That's another idea. What is the sensors and the cameras available in the market to allow you to prove the concept first? And then if it is not, then you produce that first. I know we have a camera, it's infrared camera that can detect the heat. We take advantage of it to have an application. Okay, but if there is a camera or sensors for it, go ahead. And when you do it, we'll learn.
Yeah, thanks, Summer. This was really nice work and really interesting. My question is about the stop sign. Maybe because I didn't drive in Texas for a few years, so I forgot how crazy people drive there. But I'm wondering why you don't just always have it flashing, right? If you can harvest maybe a combination of solar energy and thermal energy from tire pavement interaction, why does it need to have a camera sensing that there's a vehicle approaching if it could just flash all the time?
Very good question. Very good question. And this is the current mitigation that we have. A solar panel connected, a flashing beacon turns all night. First, it is a waste of resources because you let it to turn on at no need. Because you've seen the intersection, for example, very low traffic. The perspective of the driver, I'm a driver, okay? If I see something, and this is a continuous driver, let's say I'm not only a visitor to this area, I'm a continuous driver to this intersection at the whole time. which eventually I should learn that there is a stop sign in there. But when only the flashing beacon is gonna flash on a driver coming to it, I guess I get a message that something is weird coming. If this becomes part of the stop sign that's flashing, it loses the reflex of a driver that this is something only happens when I come in. So it will drag my attention. This is just, I need maybe to have human expertise into how that perspective would be, but as a driver, I can tell you. If I'm driving and I see only flashing light everywhere I'm light, I wouldn't take my attention. But if I only coming in and all of a sudden something flash or change, I will wake up. And usually I sleep in these areas. That happens many times. But that something is gonna attract my attention. I guess that's our perspective of the whole idea. Yes.
Sandra, I wasn't sure about the battery that you have in the piezoelectric sensor, because the piezoelectric sensor is taking the energy and change it to electricity in a way. So why it's not self-powered or can have it self-powered? Because one of the concerns you have is the life of the battery, right?
Yes.
So why don't just use it as a self-powered?
Good question. I could use the piezoelectric and I bypass the batteries. As far as I have traffic loading all day long, even at night.
Yeah.
The only reason I have to have a battery, if I don't have the same number of traffic to allow the sensors to operate in the time I don't have traffic. And I need that. So one way we did to minimize and work with the capacity of the battery that we have, we sleep the system and we wake it up only when the vehicle approaches. But I have to have a battery in case I don't have sunlight for a day. So I don't want to have the system to shut down at any moment. So the battery is only as a backup battery to serve the power that allow the sensors to operate at the time I don't have traffic or I don't have sunlight.
Excellent, but can't you have maybe a wire that is going to go back, which takes the energy and change it to electricity on the side? I can have an extra wire that is going to go to the system, and that's where I connect it with the power. So because this is a concern, if you're going to have a system like this, which is going to be very durable, but its survivability based on a battery.
Right. But again, our approach completely was based on cut the cord.
Yes,
Of course. The whole concept is I don't want to build an existing, which already available the way in motion. It has a power system that's connected to it. Our idea is to cut the cord. We're going to live in a society that everything is wireless. Right. So we really have to be in the same mood with that. We don't have to have wires. Yes, we work on the pavement instrumentation, the wires work perfectly. I want to minimize the problem that DOT always have. Minimize the interference with pavement as possible. Okay, so wires, I take it out. Now I have a system. Okay, I don't want to put it under. I did the same question when I think of why. What is the first comment I got from TechStuff when you see something like that? You think about it and you let me know. And we're all pavement engineers here. Oops, no, right here. You think about it and you let me know. You should figure it out right away. Once they saw this, they dropped the ball. But they dropped the ball for us, but it allows us to change our concept and our applications. And it was really shocking after 2 years of work. But it allows us to change the way we look into this from their perspective. And that's why communication is a key. Always work with your clients to see what they exactly do along the way. Not surprise them with a product at the finish line. Communication.
Right, guys, I think we're out of time. So let's thank Professor Dessouky for we do have the meet and greet now for the students if they want to stick around and ask more questions or interact.
My pleasure.